Welcome to Chem Time.
Hello viewers, welcome to the presentation. In the last presentation on first law of thermodynamics to a closed system, a mathematical equation is formulated that relates the change in internal energy delta U with the heat and work interactions Q and W. In this presentation, we'll focus on calculation of the change in internal energy, the Q, the heat, and W, the work interactions, for an ideal gas undergoing reversible changes. The reversible changes are shown for different processes, and this presentation is useful to mechanical, chemical, agricultural, petroleum, and chemistry students. We start the presentation by highlighting the importance of today. Today, in the year 1796, on June 1st, Nicholas Carnot was born, and Sir is the father of thermodynamics, and he is the one to introduce the word reversibility. And today's presentation focuses on that particular reversibility only. In the presentation, a parameter called enthalpy is defined and is calculated as U plus PV. And we also define specific heat at constant volume and specific heat at constant pressure for a gas. The specific heat at constant volume is denoted as CV and is given by dou U by dou T at constant volume, that is differential change in internal energy or a differential change in temperature at constant volume. And the change in internal energy can be calculated as delta U is equal to N integral CV dt. N is number of moles and CV has to be in that case joules per mole Kelvin. The specific heat at constant pressure is denoted as Cp and is given by dou H by dou T at constant pressure, that is differential change in enthalpy for a differential change in temperature at constant pressure. And the ratio of specific heats is gamma and that is given by Cp by Cv. For ideal gas, Cp minus Cv is equal to R. R is gas constant. For monoatomic gases like helium and argon, Cp is equal to 5 by 2 R. For diatomic gases like oxygen and nitrogen, Cp is equal to 7 by 2 R. The change in enthalpy is calculated as delta H is equal to N integral Cp dt. The work can be calculated as W is equal to minus integral PdV. The processes which we assume to be reversible can be categorized into polytropic, isothermal, isobaric, isochoric, and adiabatic. Whenever the word iso comes, it refers to constant. That is, isothermal means constant temperature, isobaric means constant pressure, isochoric means constant volume, and adiabatic means no change in heat. And polytropic refers to neither isothermal, nor isobaric, nor isochoric, nor adiabatic. The work, the heat, and the change in internal energy and the change in enthalpy are tabulated in the table. And anybody interested in these derivations can mail to us. We'll explain in detail. And all these five processes can be represented by a single equation, that is PV to the power of N is equal to constant and N is equal to polytropic index. If N is equal to 1, it is called isothermal. If N is 0, it is called isobaric. N is infinity, it is isochoric. And N is gamma, it is adiabatic. But the real processes are reversible and therefore they can influence the heat and work interaction terms only because the change in internal energy and the change in enthalpy for an ideal gas are dependent only on temperature and they are point functions. When work is done irreversibly, as in the case of a compression of a gas, we can calculate the actual work as work of reversible process divided by efficiency. And when work is to be extracted, as in the case of an expansion of a turbine, the work extracted can be calculated as actual work is equal to work of reversible process by efficiency. The above five processes for that matter can be represented on a PV diagram. We have shown it separately and a single diagram for all the 5 processes. Now, coming to the polytropic process, which is neither isothermal, nor isobaric, nor isochoric, nor adiabatic, and most of the industrial examples fall into this category. They are neither isobaric, nor isothermal, nor isochoric. For example, gas is compressed in a compressor. There are heat losses from the system to the surroundings, and this is a polytropic process. Similarly, when a gas is heated in a piston cylinder arrangement with a spring as shown in the diagram, the process becomes polytropic. Similarly, when blowing a balloon in hot sun also falls under the category of polytropic process. We have taken a problem related to polytropic process and we have shown how to calculate the polytropic index as well as the specific work and the change in internal energy. The problem is air is compressed polytropically from 101.3 kPa and 300 Kelvin and is delivered to a container at 2000 kPa and 700 Kelvin. Calculate the specific work of compression and change in internal energy. The equations for a polytropic compression as well as the adiabatic compression remain the same, but only difference is in case of polytropic compression, N comes into picture, and in case of adiabatic compression, gamma comes into picture. For the case of polytropic compression, T2 by T1 is equal to P2 by P1 whole power n minus 1 by n, where T2 refers to the temperature after compression, T1 is temperature before compression, P2 is pressure after compression, and P1 is pressure before compression. With the values given, T1 is equal to 300 Kelvin, T2 is equal to 700 Kelvin, P1 is equal to 101.3 kilopascal, and P2 is equal to 2000 kilopascal. When you substitute these values in the equation for polytropic process, we get N is the only unknown is N, and that is going to be 1.4. Using the value of 1, we can calculate the specific work of compression as R into T2 minus T1 by N minus 1. If you take R as 8.314 joules per mole Kelvin, it has to be converted into joules per kg Kelvin. And this is done by dividing the R value with the molecular weight of air, and then it becomes a gas constant for air. And R works out to be 287 joules per kg Kelvin. The calculations are shown. So with this, the work of compression, the specific work of compression becomes R into 287 joules per kg Kelvin into 700 K, that is T2, minus 300 K, that is T1, by 1.4 minus 1, that is 28700 joules per kg, that is 287 kilojoules per kg. The specific change in internal energy is calculated as delta U is equal to Cv into T2 minus T1. For air, it being diatomic, the Cv is equal to Cp minus R, and Cp is 7 by 2 R minus R, that is 2.5 R, that is 2.5 into 8.314 into 1000 by 29. That works out to be 717 joules per kg. With this, the change in internal energy becomes 717 joules per kg into 700 K minus 300 K, that is 286800 joules per kg, that is 286.8 kilojoules per kg. Using the first law of thermodynamics, we can calculate the heat exchanged is Q is equal to delta U minus W, that is 286.8 minus 287, that is minus 0.2 kilojoules per kg. That is heat is negative, that is heat is added from the system of compressor to the surroundings. We have taken one more problem given in recent IIT JEE examination, and this problem reads: the specific heat capacity of a substance is temperature dependent and is given by C is equal to KT, where K is a constant of suitable dimensions in SI units and T is the absolute temperature. The heat required to raise the temperature of 1 kg of substance from minus 73 degrees centigrade to 27 degrees centigrade is Nk. What is the value of N? This is given in IIT JEE 20 very recent IIT paper. Now, given temperatures are to be converted into Kelvin by adding 273. So, T1 will be minus 73 plus 273, that is 200 Kelvin, and T2 is 27 degrees centigrade, that is 27 plus 273, that is 300 Kelvin. Mass of the object is given as 1 kg. Since the units of specific are joules per kg Kelvin, we write the dimensional analysis of the equation given C is equal to kT. C is kilojoules per kg Kelvin. K we don't know the dimension, and temperature is measured in Kelvin. With this, the units of K work out to be kilojoules per kg K square. The heat required is denoted as Q and is calculated as Q is equal to M integral T1 to T3 C dt. Since C is temperature dependent, we cannot take C outside the integral. And with the values given, we can calculate as Q is equal to 1 kg, T1 to T2, 200 to 300, and C is kT. So replace C with kT and integrate it. And we get 25,000 K. So, but it is given as Q is equal to Nk. Comparing equations 1 and 2, we get the value of N as 25,000 kg into K square. This is the problem given in recent IIT JEE examination. With this, we conclude our presentation. Thank you. Request you to like, share and subscribe my channel.